Aloha, I'm Roger Brewer with the Hawaii Department of Health. You're listening to a webinar entitled Use of Active and Passive Soil Gas Samples to Support Vapor Intrusion Investigations. Our two speakers today are Martin Smith of Cox Colvin and Harry O'Neill of Beacon Environmental. This is actually the second of a two-part series on vapor intrusion. The first webinar was given by myself on February 18th. Entitled Dungeons, Dragons, Pica Houses, and the Need for Alternative Vapor Intrusion Screening Tools. Now this webinar gave a basic overview of vapor intrusion. We also reviewed a paper that we recently published entitled Estimation of Generic Subslab Attenuation Factors for Vapor Intrusion Investigations. That was written by myself and Josh Nagashima in Hawaii Department of Health. We also had three co-authors, Mark Rigby of Parsons Corporation, Martin Smith, again of Cox Colvin, and Harry O'Neill, again of Beacon Environmental Services. Now before we get started with the presentations today, I want to give a quick overview of the first webinar as an introduction to the need for better soil gas sampling that we'll talk about. First, to give a quick overview of vapor intrusion. Due to heating and wind effects, the inside of a building can become underpressured relative to outdoor air. What this can cause is the leakage of outdoor air into the building, as well as the intrusion of vapors up through any gaps in the slab of the building. This is simply referred to as building leakage by building ventilation engineers. The degree of leakage can vary dramatically between different climate regions based on how the building is heated on a yearly average and ventilated on a yearly average. One point to make is when the buildings are air conditioned, the lower floors of the building can become overpressured. So essentially you'll get minimal to no vapor intrusion under this scenario. Now the assumed magnitude of attenuation of vapors as they intrude into a building is a key part of any vapor intrusion screening investigation. That's what we're going to look at, what we looked at in the first webinar. There are two methods used to estimate subslab attenuation. We'll start with the second method. This is the method that's being used quite a bit these days. It's based on the USEPA's Vapor Intrusion Database. This is a database they tested the indoor air and subslab vapors from thousands or around 1,000 buildings, mostly across the northern United States. In this case, your subslab attenuation factor is simply the ratio of the concentration of the VOC in indoor air divided by the concentration of the VOC in subslab soil gas. And intuitively, this is very simple and should be very straightforward. But one thing to keep in mind here is for almost all of the examples in the database, they collected a single sample of indoor air and a single sample of subslab soil gas. An important thing to remember is the location of vapor intrusion entry points in almost all of these structures was unknown. So for this method to be applicable and to be valid requires an assumption that the subslab vapor plume was homogeneous. If this is the case, then the size and location of the subslab vapor sample isn't really important. You'll get the exact same subslab attenuation factor no matter where you collect your subslab soil gas sample. Now what we've discovered since then is quite a different picture. The vapor plumes beneath building slabs actually tend to be very heterogeneous, with the concentration of VOCs within any given part of the plume varying by 1 to 2 orders of magnitude or even more. Under this scenario, the size and location of the subslab vapor sample suddenly becomes very important. So your calculated subslab attenuation factor can vary quite widely depending on where that subslab soil gas sample was collected. For example, in this sketch, we assume the vapor plume has the highest concentration of VOCs under the center of the slab. If you collected a soil gas sample in this area compared to indoor air, then you would think you're getting quite a bit of attenuation because you go from very high concentration to a very low concentration. So you get a very low attenuation factor. Now compare this to collecting a soil gas sample in the green part of the vapor plume at the edge of the buildings. In this case, concentration of VOCs in the vapor plume is very low. And when you compare this to your indoor air sample, you may think you're getting very little attenuation or even no attenuation. This is actually seen in the US EPA's Vapor Intrusion Database. So this is probably a much more realistic scenario of what's going on in the subslab vapors and with US EPA's database and their estimation of attenuation factors. Now imagine for a minute what the distribution of potential attenuation factors would look like if under this single building you collected 1,000 small subslab soil gas samples. Or imagine if you did the same, if you collected a random soil gas sample beneath 1,000 buildings that looked exactly like this. So what would the distribution of attenuation factors look like? Well, it would look something like this. This is the graph of the frequency of attenuation factors for each one of the soil gas samples combined, compared to the attenuation factor at the bottom. So an attenuation factor of 0.0001 represents around a 10,000-fold attenuation of vapors. Attenuation factor of 1 represents essentially no attenuation of vapors. The same concentration of VOCs and subslab soil gas sample is detected in indoor air. So you'd see a hump in the middle around one of the attenuation factors. This represents where most of the soil gas samples were collected. Now, if you can assume your vapor entry point was somewhere within this region, then the median within this area might actually represent close to the true subslab attenuation factor for that building, for that group of buildings. On the left side of this hump, though, you'd get representation of attenuation factors based on soil gas samples collected from higher concentration areas of the plume. So in this case, again, you're seeing a false high attenuation of vapors. On the right-hand side of the graph of the hump, you'd get a host of attenuation factors representing subslab vapor samples collected from lower concentration areas of the plume. Again, to the left and to the right, these are both artifacts of vapor plume heterogeneity. They aren't real attenuation factors. So really this is actually the purple line here within this graph is the actual frequency of attenuation factors reported in the USEPA vapor intrusion database for subslab soil gas samples in indoor air. This is probably the most reasonable interpretation of their attenuation factors, is that the median attenuation factor, while it might be real, you can't trust the attenuation factors on the right-hand side or to the left-hand side of the median. They're probably just artifacts of vapor plume heterogeneity. So as a whole, the database really isn't valid for use in screening in vapor intrusion investigations beyond the possibility of the median value. We discussed this in our paper. So really we're back to method 1. And this is the original method incorporated in USEPA's vapor intrusion models and still used today. Under method 1, the subslab attenuation factor is calculated as estimate of the vapor entry rate into the building divided by the indoor air exchange rate for that building. So for example, if we assume a vapor entry rate of 5 liters per minute, which is the default most commonly used now, an indoor air exchange rate of 5,000 liters per minute, both of these for a 100 square meter building, this would generate a subslab attenuation factor of 0.001, or a 1,000-fold attenuation. Now these attenuation factors and vapor entry rates, indoor exchange rates, are going to vary widely between different regions of the U.S. based on climate. In areas of the U.S. where heating is used, more often you're going to have a higher vapor entry rate and a lower indoor air exchange rate averaged over the year. Now we use this approach to split the U.S. into 4 different vapor intrusion risk regions. Region A, which is the highest risk for vapor intrusion, represents the cold northern states of the U.S. Region B, it's more warmer climate, represents more moderate risk vapor intrusion. This includes the southeastern U.S., the southwestern U.S., and the northwestern coastal area. Region C represents the Mediterranean climate of coastal California. It has a lower risk, even lower than Region B. Region D represents the tropical areas of Hawaii and Southern California. Now again, based on radon studies and building ventilation studies and models, we assigned a vapor flux rate or vapor entry rate to each one of these regions, and also a default indoor air exchange rate to each region. And then we use the ratio of those, the vapor entry rate and the indoor air exchange rate for each region, to calculate a default subslab attenuation factor. As you can see at the bottom here, that the default attenuation factors don't differ that much. We estimated a default attenuation factor for region A, the coldest area, of 0.003, or a 300-fold attenuation, whereas in the tropical regions, region D, we estimate default attenuation factor of 0.0005 or a 2,000-fold attenuation. So only about a difference of 6 or 7. Not that great, but still worthwhile noting, and again driving home the point that a single attenuation factor can't be applied to all of the U.S. as a whole. So that was just a quick overview of the paper we published and also of the first webinar. You can find a recording of the full webinar on this webpage below under the What's New section of the HEER office's webpage. And we use this as a setup for the need for a really better soil gas sampling beneath buildings. And what's really needed is more samples and or bigger soil gas samples beneath slabs. This figure here just gives you an example of the area represented by a soil gas sample of sizes typically collected today. And now when you start thinking about potential subslab vapor plume heterogeneity, and really think about what these samples mean, how useful are they? One approach we've seen used is to collect 50 milliliter samples, really tiny soil gas samples, with the idea that you're going to catch the hot spot beneath the slab. Well, in reality, the chance of that is negligible. A 50 milliliter soil gas sample, if you assume that 20% porosity and that the soil gas sample is coming from the first 15 centimeters underneath the slab, only represents an area of around 2 centimeters in radius, whereas a 100 square meter area of a slab 15 centimeters down in the fill material, if you assume again 20% airfield porosity, would represent about 2,000 or 3,000 liters. So a 50 milliliter sample collected from this large volume of a plume really isn't going to tell you much. A 1 liter sample in reality isn't much better. It would only represent a radius of influence of around 10 centimeters. 6 liter samples, you'd get a radius of influence of around 25 centimeters, just to give you an idea of how big these samples are compared to how big the vapor plume probably is. So this is the typical size of soil gas samples collected. I think what we really need is a lot bigger samples. A 50 liter soil gas sample still only represents an area of influence of around 50 centimeters if you assume that all the vapors are coming from the top 15 centimeters of fill material under a slab. I'd love to see something like 100 liter soil gas samples from collected under slabs, or even bigger than that. But still, even then, you're only getting out to about a 1 meter, 100 centimeter radius of influence. So it's still not that big, but definitely much better than a 50 milliliter or even a 1 liter sample. I'm not sure how to do that. Right now, we're just looking at collecting more samples underneath the slab to get a better idea, a better resolution of vapor plume heterogeneity beneath slabs. So that gets us to today's webinar. It's titled Use of Active and Passive Soil Gas Samples to Support Vapor Intrusion Investigations. Again, we have two presenters, Martin Smith with Cox Colvin and Harry O'Neill with Beacon Environmental. Martin is going to talk to us about active soil gas sampling, and Harry O'Neill will talk to us about passive soil gas sampling. So a quick intro. Cox Colvin, where Martin Smith works, the developers of vapor pens. This is how I was originally introduced to Martin. If you're not familiar with them, these allow for a cheap and much more cost-effective means of collecting soil gas samples beneath slabs. So you can collect lots of samples for the same cost. This allows you to get a much higher resolution of what the vapor plume looks like under the slab. So Martin's a geologist, and he's a lead for the Vapor Intrusion Group with Cox Colvin. He's worked for over 20 years in environmental work. Prior to Cox Colvin, he worked as a radon investigator for the Ohio EPA, and prior to that, like I think a lot of geologists, he was an exploration geologist for Shell International. Harry O'Neill is the president of Beacon Environmental Services. They're an accredited laboratory and field sampling company that specializes in soil gas and indoor air investigations. So Harry's worked on well over 1,000 sites in multiple countries. He's been at the forefront on the use of passive soil gas sampling technologies, both within and outside of the U.S. And he's one of the co-authors. ASTM standard was D7758, the standard practice for passive soil gas sampling. And similar to vapor pens, the passive soil gas samples are much cheaper than active soil gas samples, and they allow you to collect a lot more samples for the same cost, so you get a much better resolution of what the vapor plume looks like. So without further ado, I'll hand the presentation over to Mort, and then we'll move on to Harry. Thanks.